Our last talk for the session today is given by Helen Quinn. Helen Quinn is Professor Emerita of Particle Physics and Astrophysics at SLAC National Accelerator Laboratory. She received her PhD in physics at Stanford in 1967, has had a long and impactful career in theoretical physics, resulting in many major advancements, including collaborations with Howard Georgi and Steven Weinberg on unification of forces in the Standard Model, and her work with Roberto Pache to develop the Pache-Quinn symmetry as a means of tackling the strong CP problem. Helen Quinn has taught physics at both Harvard and Stanford. In addition to her numerous contributions to theoretical physics, she's played a major leadership role in expanding physics to the wider community. Her contributions have earned her numerous awards and honors, most notably the Dirac Medal and the Compton Medal. In 2001, she was elected as president of the American Physical Society. In recent years, Helen has played a central leadership role in the science education studies, and leading to the development of several national study groups for science standards for K-12 education. Today, Helen Quinn will talk to us about her work in CP violation, a topic which to me seems to be as rich in promise and puzzles as it ever has been. Please join me in welcoming Helen Quinn.
Thank you very much. Well, I don't know why CP violation belongs in an astrophysics and cosmology section, except perhaps the connection that Rocky has already talked about. And I'll come to that towards the end of my talk. I am not talking about my work. I am talking about the work of many, many people. And I'm going to, just for fun, start by going backwards and thinking about how particle physics looked 50 years before the Standard Model, or actually 40. So the way we think about particle physics today is as simple as I tell it to non-physicists. We have to explain what exists, and we do that with a set of particles. We have to explain what happens, and we do that with a set of interactions. And we have to explain what can't happen, and we do that with a set of symmetries, or rather the conservation laws and forbidden processes that come out of those symmetries. And of course, CP is one of those symmetries, but it's not exact. And not exact symmetries are also very interesting because they put limit. It means some process is small compared to everything else. And we still have the fact that it's visible because it's special, it's breaking a rule that everything else has to obey. Okay. So let's go back to when Dirac wrote his equation, because I think of that as kind of the beginning of particle physics. Before that, we certainly had quantum mechanics, we certainly had relativity, both special and general, and we had some idea of a nucleus, but actually we didn't have any idea of neutrons, or they were just beginning to be talked about. Do you know when Pauli suggested the neutrino, he called it a neutron? What we now call so there was some neutral particle. So obviously the idea of the neutron as we know it today wasn't strongly established. That was 1932 when that came out. So Dirac knows of two particles, and he's trying to write an equation that gives correct properties and includes relativity. I mean, the Klein-Gordon equation, or if you like, Schrodinger's equation already existed. It was relativistic, but it had some problems, and Dirac thought there's a way to answer those problems and wrote this new equation. What is spectacular is that the mathematics of this equation predicted something that Dirac could not have imagined and did not like. It said there were positive particles as well as negative ones, and it was uncomfortable because even 2 years later, when it was very clear, originally Dirac said, oh, maybe that's the proton. He knew perfectly well that there was a symmetry that said the masses had to be equal. But he said, well, maybe the higher order corrections, I have no idea what higher order corrections he was talking about, will fix that mass problem. But when Oppenheimer and Tamm talked about annihilation, well, if a proton and an electron can annihilate, there's no stable hydrogen. So there's no stable matter around. And so that's clearly a disaster. It cannot be the proton, just for physical reasons, not for symmetry reasons. And so they had to predict this thing called the whole. Why was it called the whole? Because we're before second quantization, so we're filling the negative energy sea of states, and the positive particles are then the holes in the negative energy sea. That's still a good notion in condensed matter physics today, but with second quantization we get rid of the negative energy sea. And matter conservation is gone because of these annihilation processes, but we do still have lepton and baryon conservation. We have P and T as symmetries, and a new discrete symmetry C, because once you have you have to have antimatter and matter before you can have a symmetry between them, right? So this is 1932. We've discovered, Anderson has discovered that there are indeed positrons in cosmic rays, and this is, I would say, an early stage of particle physics. Particle physics really takes off once we get accelerators and it becomes high energy particle physics. But we're still starting to move in that direction. I want to comment on how Pauli's comment. Pauli says, this is after the discovery of the positron. He says, I don't believe in the whole theory because I would like to have the asymmetry between positive and negative electricity in the laws of nature. It does not satisfy me to shift it to the initial state. Now, I think he was not talking about the universe. I think he was talking about, he did not like the negative energy sea, and he wanted positrons to be particles like electrons, and then some physical reason why we saw a lot of one. So I think this is the beginning of the question of baryogenesis, even though that's not what he was actually talking about at the time. Of course, field theory fixes the problem that was bothering Pauli, but it doesn't fix the problem of initial states. Okay, also about this time, there's the neutrino and there's the neutron. Right, these are big steps forward because obviously without neutrons there's no nuclear physics. I mean, if you don't have neutrons, you can't even begin to make decent models of nuclei. But new particles required new interactions because people started to think about nuclear physics. There was necessary a force between neutrons and protons, and of course there was also radioactivity, known since well before. So the question of what were those decays needed the weak interactions, among others, because of course there are also strong fission processes. So the Fermi theory for beta decay comes along for about this time, and the Yukawa theory for strong nuclear forces. So beginning to have the kinds of theories we would recognize today, and underpinnings of the standard model, I would say. Of course, we no longer think about Yukawa interactions for strong nuclear forces. Well, in effective field theories you can to some extent, but certainly we still strongly use Yukawa's ideas in the standard model. There are a lot of Yukawa couplings in the standard model. In 1956, weak interactions were found to be parity violating. That was actually the first time somebody looked for it, because for a while people had just sort of assumed it must be parity consuming until the question came up. Li and Yang looked at the data and said, actually nobody's tested that. And so Wu tested it, and very quickly thereafter Gao and Lederman, and I forget who the third author is. So
Weinrib.
Okay. And this says, okay, parity is not a symmetry, but it still looks as if CP is a good symmetry. Field theories say CPT is a good symmetry, and it seems CP and T, with this data, can still be symmetries of the theory, and we get to the V minus A theory of the weak interactions. The experiment drives the theory, in this case, for a number of steps, right? The experiment drives parity violation into the theory. Experiment drives CP violation. When Christensen, Krohn, Fitch, and Turley observed that neutral K mesons are not CP eigenstates, that tells you there must be some CP violation in the theory. Because if it's a symmetry, the eigenstates of the theory must respect the symmetries of the theory. But essentially, nobody knew what to do with this, because it actually was hard to write a theory with CP violation with the then known particles, right? As Steve Weinberg taught me many, many years ago, CP violation requires interference. That means it requires coupling constants with different phases. And simply requiring homoticity, for example, makes the electromagnetic coupling real. Furthermore, when you start to add other couplings, by redefining the phase of a field that's involved in the coupling, you can redefine the phase of a coupling. And as long as you have more fields to redefine than you have couplings, you finish up with a real Lagrangian, no matter what you started with. You write down the most general Lagrangian, and you can remove CP violation. So in order to explain this experimental result, you would have had to make up a lot of particles to be able to write a complicated enough theory to have CP violation, and everybody ignored the problem. It's a small effect. There are lots of other things we didn't understand. So let's put it on the back burner, worry about it later, and continue write theories that have CP. Meanwhile, Sakharov, which Rocky told us about, the three conditions, the loss of thermal equilibrium, as Rocky says, not so explicitly there, but implicitly there. And actually, there's two losses, right? One is the loss at the time of baryogenesis, and the other is afterwards. We can have some process which creates an imbalance between baryons and leptons, but if the baryon number changing processes to continue to be active when thermal equilibrium is reestablished, because the masses are equal, the equality will be reestablished. So any inequality only lasts if not only during the transition there's some kind of process that can generate the baryon number, but after it. And that is one of the things that the Standard Model does very well. We do know that in low energy Standard Model situations, baryon number is a very good quantum number, even if not exactly conserved. So the after part is really not a problem, as long as you generate the baryon number late enough. If you generate it early, you have to worry about this. Okay, this is, I guess I already said what I've put on this transparency, so I won't stop for it. Let's get to what we're really talking about here, the Standard Model. Now, this was already mentioned that the initial idea that you could do this in the Standard Model, in fact, you have just enough degrees of freedom for one CP violating parameter in the Standard Model if you have 3 generations. And if you only have 2 generations and 1 Higgs doublet, you don't have enough parameters. Now, as soon as you add additional Higgs doublets, you can do it with 2 generations. So the statement is you couldn't do it with 2 generations is not true. But you couldn't do it with 2 generations and 1 Higgs doublet. So that's a suggestion that 3 generations might be an interesting theory, and they wrote down what that theory looked like. So, but you can also add scalars, and as you've heard in the talk on baryogenesis this morning, people are playing different games with adding scalars as ways of generating baryon number. Finally, of course, we get to November of 1974 when CHARM appears, and in the analysis of those same data over time, tau also, which is the first particle of the 3rd generation. So 3 generations becomes the Standard Model. And in the 3 generation Standard Model, we have this matrix. And what is this matrix? It's the matrix which relates the weak eigenstates to the mass eigenstates. There are the quarks which pair up as doublets of the weak interactions are different pairings than the quarks which have definite masses. So if we make the top quarks the ones we know, the bottom quarks will be linear combinations of the mass eigenstates. And this matrix tells you what those combinations are. The diagrams on the left are to say, It's not as easy as it might look to you might think to measure these constants, because of course we don't observe quarks. We observe mesons or baryons or physical particles, except in the case of the top quark decay, we're always looking at that decay inside some strongly interacting particle with strong interactions internal. And of course, at the top quark, we're looking at a top produced in a strong interaction event with an antitop, but we're looking at the decay of one of them. And so we have to dig the weak interaction process out of strong interaction physics that surrounds it. And so the process of getting to values for each of these parameters is a thing which, again, like many of the things we've been talking about today, the interplay of data and theory over time gets you to more and more accurate data, accurate values for these parameters. The other thing which is noticed about these parameters is it happens, and we have no explanation as to why this is so. This matrix is 2 first order in a small parameter, diagonal, and the off-diagonal terms get smaller as you go more off-diagonal. And that's noted in the Wolfenstein parameterization of these quantities by calling the off-diagonal, the first off-diagonal element lambda, and the next one is lambda squared times some close to 1 numbers. The other thing about this matrix, I said there's 1 parameter left. The conventional place you put it is in the upper left and lower right elements. That's just a matter of choice of phasing of the fields, but that's the convention. Unitarity gives us a constraint. There's not 9 parameters, there's only 4. And those parameters can be written as the ratios of these matrix elements, the overall Fermi constant, and that 1 phase for the corner. So for the ones that one is complex, and the conjugate phase, of course, enters by the unitarity constraint. Now, unitarity is, say, a statement that a sum of 3 complex numbers adds up to 1. That, of course, makes a triangle in the complex plane. And so we talk in B physics, people talk all the time about the unitarity triangle. That is simply the set of relationships between these quantities required by unitarity. And testing the standard model in this flavor physics domain is measuring all these quantities and checking that they fit the relationships demanded by unitarity. And because we have different ways of measuring, several of them, also checking that the different ways of measuring give you the same answer for the same parameter. So it's just like the other concordance models. We have many more measurements than parameters, and the game is to see if they fit, or actually, as the B factory was being built, to see if you get any deviations from the relationships expected in order to look for beyond standard model physics. In fact, as it turned out, it all fits remarkably well. Now, there are 3 kinds of CP violation, if you like. I already talked about mass eigenstates, which are not CP eigenstates. The next one is a rate, and a rate for the CP conjugate process. That means turn all particles into antiparticles and all antiparticles into particles, and look at those 2 processes and see if they have the same rate or different ones. And the final one is a special case, again, for the neutral but flavored mesons. You can take a flavor-tagged initial state, decaying to a CP eigenstate final state, and ask, is there a difference between one flavor and the complementary flavor, the antiparticle, the B0 or the B0 bar, in the decay? And it should be a time-dependent difference, where the time is the time between when the tagged particle decays and when the CP eigenstate the particle that decays to the CP eigenstate decays. So those are the three kinds. And the last one is particularly nice because it gives us cases where the strong interaction physics factors out, and we have a pretty clean measurement of the angle in the unitarity triangle that relates to that decay. So two accelerators and one detector for each accelerator were built. We refer to them as Bar and Bell, but remember that without PEP2 and KEK-B, Bar and Bell wouldn't be very useful. So the accelerator physics was important too, and having two rings with two different energies was important. So you made a coherent BB bar state, but moving. And that was, because it was, if it was still, one particle decays, the other particle decays, you have no idea of the time difference between those two decays. But because it's moving, one particle decays, the other particle decays, the distance between the two decays tells you about the time difference between the decays. So that was very important to have the asymmetric rings, and to have two different rings and bring them in collision made it a little more complex than just a single E plus E minus ring. But it was done, and these are the two, and then the detector is a standard multi-layer detector built and designed to have the sensitivity to look at the modes we knew needed to be studied. Here's where the theorists came in. Right, if you go look at the Babar physics book, there are a lot of theorists who contributed talking about what were the different modes that would be interesting to detect, what sensitivities you would need to detect those modes, and therefore the detectors were designed as much as possible to be able to look at all the interesting cases. So there's another interplay between theory and experiment is these arguments about predictions can guide the design of the experiment and put constraints on what the detectors need to be able to do. And then the experimentalists have to be clever to be able to do that, and they were clever. And there's new technologies in these detectors. Now they've been there. These machines started running 1998, 99. Two first papers were published in 2001. So they've now been running for some time. Each of them has published over 500 papers. Not all of those papers have to do with CP violation or even with B decays, but many of them do. And of course, the measurements over time have gotten better statistics and better, which we display by plotting these triangles. Now again, this is a concordance model, so we have to look and see, and I'm just stealing this slide, as I didn't mention that when I showed you the detectors, but both that slide and this one I stole from David Hidlin, or rather he sent them to me because I asked him to. Because it's very beautiful, and he had it all laid out in his Panofsky Prize talk in 2016, and it hasn't changed much since then, so let's look at it. So if we look in 1995, what we have is the difference of masses between the two D mesons, the difference of mass between the two, so the K mesons, we're looking at the K mesons and the D mesons. We're looking at epsilon K, which is that CP violation in the difference of the mass eigenstates of the K mesons. It's hard to calculate from theory to relate the measurement to the underlying parameters. That's the main reason why these bands are big. It wasn't that epsilon K was not accurately measured, it simply wasn't able to be accurately calculated. But you see, there is a triangle. There's definitely there is a CP violation, which is shown by the fact that the area of the triangle is non-zero. The area of the triangle is related to that Yarlskog parameter that appeared in Rocky's talk, the J, which is the one CP violating quantity in the standard model. And that was so that's the pre-B factory. The 2001 is the first B factory measurements, and the sine 2 beta is that decay where you have one tagged B and one CP eigenstate decay of the B, and you look at the time dependence, and that gives you a measurement of the angle which is at the right-hand vertex of the triangle. And because you're measuring sine 2 beta, you get a fourfold ambiguity in what that angle is, but you put it on top of the other data, and it begins to limit the area of the vertex of the triangle, which is the interesting thing we're trying to discover. Right? 2004, we have this other thing called alpha. If you look carefully, you see the upper vertex of the triangle has an angle called alpha. How did we measure alpha? That takes a different set of B decays, which are dependent on that parameter. And those B decays are more complicated to calculate because in addition to a straightforward process that gives you that decay, the decay is B to pi pi, right? There are penguin diagrams. You heard that term before, as well as the simple diagrams that contribute to that decay. And calculating the relative strength of the penguin diagrams has some arbitrariness. But there's more than one B to pi pi decay because there's more than one charge of a pion. And so there are isospin relationships between the different decays. And this penguin diagrams have a different isospin structure than the other diagrams. So if you can distinguish the different cases and measure those multiple decays, you can have a way of sorting this out. And that is what gave us the turquoise regions that are labeled alpha there begin to separately. We've already constrained beta, now we're separately constraining the angle alpha. And we go on, and as we go on, we add processes, and we refine each measurement. You can see the measurements that are constraining VUB get smaller and smaller. Most of that is lattice calculations. Right? Lattice calculations giving us better, the relationship between the measurement, the measured quantity, and the parameter requires a lattice calculation to extract the strong, to get the strong interaction part of the physics out of the problem. And so it progresses until in 2015, we're in this beautiful situation where the vertex is really very, very finely constrained. But unfortunately, it also all fits together. Fortunately for the standard model, unfortunately, if you're looking for physics beyond the standard model, you see everything we've measured up to and including today, every now and again there was a 2 sigma or a 3 sigma deviation in some relationship predicted by the standard model. None of them survived to become significant. And so, and still there are a couple of those floating around today, but in fact, the standard model has beautifully explained everything here, just as it beautifully explained the precision electroweak. So it's building one set of relationships that we've tested on another. Strong interaction jet physics, precision electroweak physics, and now CP violation physics and B decays. We have, as has been said multiple times in this session, in this meeting, over-constrained, really verified the standard model as a well-established piece of whatever the ultimate theory of physics is. And so we know anything we do now beyond this. Oh, this is another piece which is interesting because CP violation, if you're talking about a theory which automatically has CPT, implies T violation. But you want to also test for T violation to see if you're seeing the relationships that CPT predicts or not. And this is the T violation. The blue lines are the theory without T violation, and the red line is the theory with the T violation, that is implied by the CP violation that has been measured, and you see which one fits the data better. It's clear this too fits the standard model picture, that CPT still looks good, but T is definitely not an exact symmetry of nature. Right? So we have these observations, and that means we have extreme constraints on any extension of the standard model. Just like, When Einstein introduced special relativity, he did not throw out all the confirmations of Newton's laws of motion. He knew his theory had to have a limit in which it reproduced Newton's laws, as well as a limit in which it was totally different from Newton's laws, because otherwise you couldn't have a constant speed of light for all observers. So that the idea that theories disappear when new information comes along, no. The theory that we have developed and tested as thoroughly as this theory will be part of whatever theory. It may be an approximation, it may be a limit case, but it will be a piece of whatever future theory we develop in particle physics. It must be, because it has been so thoroughly examined and tested and has survived so many tests. It's going to be part of what comes next. Or whatever comes next must be able to see in what way it reproduces this theory. And it's easy to break these relationships. It's not as if it's, write down any general extension, add some particles, couple them any way you want. Supersymmetry, for example. No, the generic supersymmetry model is already ruled out because it would have all kinds of other CP violations, and it would have affected some or other of the measurements that we have so carefully constrained. So when you're writing extensions, you always have to check and make sure that the new pieces fit together with the old pieces in a coherent and consistent way, because consistency is one of the basic rules. I think, and I say this when I'm talking to non-physics people, I think what Einstein did was to see where there were inconsistencies that other people at the moment were not insisting that had to be resolved, and say, these two things are inconsistent, I have to change the theory to resolve those two things. Constant speed of light and adding velocities for special relativity, light traveling the shortest path, and light bending because of gravity at the sun, that requires curved space to be consistent. So each of these cases, we're arguing for an overall consistent theory of everything, but every time we've only looked in a certain region, so we only have a consistent theory of what we have measured to date. And as Rocky also said, there are reasons from astrophysics and cosmology particularly, and also from neutrino masses, that we have to add things to this theory. We cannot stop here, we have to go on. So I really don't need to talk about these next two slides because Rocky did a much better job than I will do. I just want to make a couple of comments, and that is, these are actually two difficult problems, right? One difficult problem is calculating that number that was something times 10 to the minus 10, that Rocky called the ratio of baryons to entropy. Rocky showed us as a measurement. The difficult calculation is relating that measurement to the underlying theory. And there's a lot of work between saying, okay, this is what we observe, and saying this is what we measure. And that work was completely buried in the talk Rocky was giving. But so that number is pretty well constrained, I think, now, and you saw that in Rocky's talk. The other one is, can we take this parameter in the standard model and calculate it? Again, Rocky told us no, and it's not even the model that was developed to use that asymmetry and generate baryon number was going through a bubble wall, but there isn't one. So this is definitely not the answer, which means there has to be something else. The CP violation that we have observed in the standard model cannot give us the baryon asymmetry of the universe. If that's the case, there's more CP violation to be found somewhere. Maybe it's in the neutrino sector, and again, Rocky talked about that case, heavy neutrinos decaying, heavy Majorana-type neutrinos decaying and violating lepton number is one of the obvious candidates. Now we know that neutrinos have mass, But there's lots of open questions there, and as Rocky said, many more ideas, but all of them require us to add something to the standard model. Another standard model CP violation, and this perhaps is another reason to talk about it. How come the strong interactions don't have CP violation? Right? We know they don't because the neutron-electron dipole moment has been looked for and exquisite limits have been set. It's like 10 to the minus 12 and shrinking. And so the question is, if there were CP violation in the strong interactions, it would generate a neutron-electron dipole moment. So we know with very strong bounds that if there is, it's very tiny. However, that's not easily explained in a theory where there are CP violations, because eventually those weak processes affect strong interaction processes by loops or indirectly. So you would induce, even if you tried to constrain, and also the notion that you can impose a symmetry on part of a theory doesn't make sense. You cannot impose CP symmetry on the strong interactions and break it in the weak interactions. Partly for the reason I just said, it will get induced anyway, but partly just logically it doesn't work. If we think of this as a single theory, then either we impose the symmetry overall or we don't impose the symmetry. Imposing the symmetry overall and having spontaneously broken CP violation has been tried, does not seem to work very well. It can't fit all the data. I would say it's pretty much ruled out at this point, but maybe you could make it work. The other answer, that it's just an accident, is also a possible answer. It just happens that that parameter is small and we don't know it. There's lots of small parameters in our theory that we don't know why they're small. But if we try to explain why this parameter is small, there's a simple answer. And that's Pachequin symmetry, as it's now called. It means we add a symmetry. And why did we pick this symmetry? Well, how do we get there? We were thinking about instantons because Gerard had been visiting at Stanford, I was visiting at Stanford, and Steve Weinberg was visiting at Stanford. This conversation had been going around. But Roberto and Roberto was an assistant professor at Stanford. So Roberto and I were talking about it, and we said, look, the theta parameter is irrelevant if any quark mass is 0. And in the early universe, it's hot enough, the quark masses are 0. So how can a theta parameter that's irrelevant become relevant? Couldn't we just tune it in some way? And thinking about that, we realized, no, that's not true, because tuning the theta parameter is doing chiral rotations on quark fields. And chiral rotations on quark fields change Yukawa coupling phases. So hidden in this high energy theory are all the Yukawa phases. And when symmetry breaking happens, those phases are going to come back to haunt you in some way as phases of the quark mass matrix, among other things. So we said, well, how can we make it so that when symmetry breaking happens, it will naturally fall to the situation where the phase of the quark mass matrix cancels the theta parameter? And we found we could do that if we added this additional symmetry. And this helped. The conversations with Steve about field rephasing were important. Actually, before we talked to Steve, Roberto and I had written a totally wrong paper, which we hadn't shown to anybody. And then we talked to Steve, and he said about 5 words, and I said, Roberto, we better go away and talk some more. So we never told Steve a totally wrong theory. But once we found the answer, we were so excited. We made a toy model and published it. We knew we had to add at least 1 Higgs doublet. Actually, that theory was ruled out quickly experimentally. And today, to get this theory, this idea to work, you have to add at least 1 Higgs doublet and 1 singlet and maybe more. Right? The surviving models have more Higgs particles. But even when you add one Higgs doublet, right, we're adding charged Higgs particles and neutral Higgs particles to the theory. And we published the paper with this toy model with 2 Higgs doublets, and we kind of knew it was going to be ruled out pretty quickly, so we didn't even investigate its phenomenology. But there's actually one piece of the phenomenology that we should have thought of, because it's a consequence of the symmetry, and therefore, whatever your model is, it will be part of the model. And Steve called me up a few days after the preprint went out and said something like this: "Did you notice that your theory predicts an almost Goldstone boson?" And my response was, after 2 seconds of thinking, well, of course it does. But no, I didn't notice that. And then Steve said, okay, well, then I'll publish it as my paper. And Frank Wilczek noticed the same thing. So the fact that it's the Weinberg-Wilczek axion and not the Pachequin axion is because we didn't look for it. We didn't think about it. We just wrote down the symmetry and said, this will fix the strong CP problem. And, but in fact, we've added Higgs particles, therefore we've added more phenomenology to the theory. And there's those charged Higgs particles too. So everybody talks about the standard model as being 1 Higgs doublet. But if you take this problem seriously, it's at least 2 Higgs doublets and 1 Higgs singlet. And there's more to find predicted by this once you pin down the parameters here. And of course, the axion searches are wonderful experiments going on, which are just reaching interesting sensitivity. They recently published a paper where they've ruled out a little bit of the region that would be the axion coupling and mass if the axion dominates dark matter. So CP violation has provided beautiful tests of the standard model. It severely restricts extensions of it. But it also provides some arguments for why we need something beyond the standard model. Thank you.
Hi, thanks. That was great. We're running a little late, but we might have time for one quick question. I think there's someone with a hand right there.
There's a hand up.
Thanks very much for that talk. I just wanted to point out with this unitarity triangle, of course, it is an amazing thing that those angles add up to 180 degrees, a tremendous victory for the B factories. But there are some problems remaining with that. You know, for example, I just point out now there may be an issue with the sides of that triangle. The VUB side, which is on the left-hand side.
The green ring.
Yeah, yes, the green ring. The VUB side is looking a little too large for that value of sine 2 beta, for example, and also, which isn't shown on there actually, and this
with the errors shown here, they're overlapping, but just. Yeah. And as you improve those errors, there can begin to be conflicts which say there's little bits of something here that we're missing. Which is the game of high precision physics, right? We have to. So I said, there's nothing yet. This doesn't mean there won't be something as we get to better and better statistics. And things occur. The other thing I didn't say, which I intended to say, is of course the B factories are not the only place Bs are produced. There's now a lot of B physics coming from LHC data and LHCb, even including B states that the B factories couldn't produce, such as B sub S or B sub C. And so that becomes another set of constraints. And maybe eventually this space will give us some violations of the standard model. And you're saying we're on the borderline of that at this point.
I think so. There's several puzzles that, you know, that are out there.
Michael wants to speak to that.
There are 2 different ways of determining VUB. There's an exclusive method which relies on basically perturbative QCD, but also has large backgrounds that have to be subtracted. The other is an exclusive method, which relies on lattice gauge theory normalization of form factors.
And there's a tension between them.
There's a tension between them. And as I understand, the exclusive method agrees very well with the other determinations of the unitarity triangle, whereas the inclusive method is deviant. So this is a problem that needs to be resolved. My money is on the exclusive method, but you may have a different opinion.
Yeah, so that it's exclusive, inclusive, and lattice calculation are all there in that game, and which one is right or wrong, that's another tension, which is at least as big as the tension you're pointing out between that and sine 2 beta, I would say. I think time is up.
Yeah, I'm sorry. I'm going to have to cut off I hate to cut off the discussion because it's fascinating, but we're already running late for lunch, and I want to thank Helen one more time for a great talk. Thanks.